There's a mysterious interstellar object hurtling towards our solar system, exciting scientists across the globe. While many think it's just a comet, some theorizing a possible alien origin due to a few curious characteristics.
The James Webb Space Telescope has once again reminded the world of its extraordinary power by capturing the first ever real image of the interstellar object 3I/Atlas. For astronomers, this marks a historic moment because this object does not belong to our solar system at all. It is a true traveler from the stars, an interloper passing briefly through our neighborhood before continuing its journey across the galaxy. Until now, images of such bodies were elusive, blurry, or incomplete. Webb's unmatched sensitivity and clarity have finally delivered an authentic, fully resolved portrait of this cosmic visitor, opening a new chapter in our understanding of interstellar wanderers. Before we start, smash the like and subscribe buttons for more updates. 3I/Atlas is the third confirmed interstellar object observed passing through our solar system. Its very designation reflects its uniqueness. 3I for the third interstellar, Atlas for the survey telescope that first detected it. Unlike the more famous Oumuamua, which ignited debates about its cigar-like or pancake-like shape, or Comet 2I/Borisov, which resembled a familiar comet, 3I/Atlas has remained shrouded in mystery. Astronomers have long speculated about its structure, its composition, and its origins. Now, with Webb's first real image, those speculations are being replaced with data, clarity, and insight. The image itself is breathtaking not simply because of its resolution, but because of what it represents. Against the dark velvet of space, Webb has caught this alien body in crisp detail, its faint coma and elongated core visible in a way ground-based telescopes could never achieve. The telescope's infrared instruments have picked up subtle signatures from dust grains and volatile gases, revealing that this is not just a dead piece of rock, but an active traveler carrying the fingerprints of a distant stellar nursery. For the first time, humanity can look directly at matter forged in another system, preserved for eons, and passing through our view for only a fleeting moment. The implications are immense. Every interstellar object is a time capsule from another star's formation process. They are messengers carrying raw materials from environments entirely different from our own. By studying the composition of 3I/Atlas, scientists can directly compare the building blocks of distant planetary systems with those that shaped Earth and its neighbors. This comparison could reveal whether the chemical recipes for planets and possibly life are common across the galaxy, or if our system is an outlier. Webb's ability to detect subtle spectral lines means that we may soon know what exotic ices or minerals coat this body, whether it carries unusual organic compounds, or if its chemistry echoes the familiar fingerprints of comets closer to home. The timing of this achievement underscores Webb's unique role in 21st century astronomy. The telescope was designed not only to peer into the first galaxies of the universe, but also to capture the faintest details of nearby objects. Its instruments have the precision to isolate the dim glow of a small body like 3I/Atlas, even when competing with the glare of stars in the background. Where ground-based telescopes struggle with atmospheric interference, Webb's vantage point beyond Earth's atmosphere allows a crystal-clear view. Without this technological marvel, 3I/Atlas might have remained a ghostly blur in the night sky, its secrets hidden. Astronomers are particularly fascinated by the shape and activity revealed in this first image. Unlike Oumuamua, whose unusual form defied easy classification, 3I/Atlas shows clear signs of outgassing, its surface shedding material as it nears the sun. This makes it more comet-like, though with significant differences. The structure of its tail, the texture of its coma, and the nature of its ejecta suggest an origin in a cold, distant region of another star system. That means Webb is essentially watching an exocomet in action. The gases being released, analyzed through Webb spectrographs, are pieces of chemical history carried across interstellar distances. There is also the matter of trajectory. 3I/Atlas does not loop around our sun like native comets or asteroids. Its hyperbolic path makes it clear that it is only visiting once. This trajectory tells astronomers about the gravitational encounters it may have had in its home system and the forces that ejected it into interstellar space. Webb's image, combined with detailed orbital analysis, allows scientists to backtrack its likely path and attempt to identify the kind of star system it came from. Was it born near a young, volatile star where planetary systems were just coalescing? Or did it emerge from the quieter outskirts of a mature system? These questions are no longer purely theoretical. They can now be tested with data. For the public, the emotional impact of this image cannot be overstated. To look at 3I/Atlas through Webb is to stare at a true outsider. It is not one of ours, not part of the familiar solar system family. It is matter born under a different sun, shaped in a different cosmic cradle, carrying in its icy shell the chemical imprint of a distant birthplace. The sheer reality of seeing it, an object that has traveled for millions or even billions of years through the cold between the stars, now illuminated for us in detail, reminds us of the vastness of the galaxy and our small but extraordinary ability to perceive it. Scientists emphasize that the study of interstellar objects is still in its infancy. Oumuamua was the first, and its mysterious nature left more questions than answers. Borisov gave clearer comet-like data but was observed with limited instruments. Now, with Webb capturing 3I/Atlas, the field has entered a new era. For the first time, researchers can combine high-resolution imagery with deep spectral analysis, unlocking a level of detail unthinkable only a few years ago. This will shape not only our knowledge of 3I/Atlas itself, but also how we prepare to study future visitors. Interstellar objects are rare, but they are not unique. Each one provides a fresh opportunity to study alien material without sending a spacecraft across light years. The fact that Webb has secured this image so early in its operational life speaks to the foresight of its design. When engineers and scientists planned its instruments, they envisioned galaxies at the edge of time, the birth of stars, and the atmospheres of exoplanets. Yet the telescope's versatility has proven equally effective in capturing fast-moving transient visitors like 3I/Atlas. Its ability to pivot between the vast and the fleeting, between the most distant and the most local, is what makes it a cornerstone of modern astronomy. On the scientific front, the image of 3I/Atlas will fuel years of research. Detailed analysis of its spectrum can reveal isotopic ratios that indicate where in a star system it formed. Ratios of hydrogen to deuterium, for example, can point to its origin in either inner or outer regions of a protoplanetary disk. The detection of unusual molecules could hint at environments unlike anything in our solar system. Even the texture of its dust grains, inferred from how they scatter light, can speak to the conditions under which they solidified. Every pixel of Webb's image carries information, and every spectrum obtained will deepen our knowledge of worlds beyond our own. There is also an emerging philosophical dimension to Webb's capture of 3I/Atlas. Each interstellar object is a wanderer that outlived its home system's immediate gravitational embrace. They are survivors of cosmic upheaval, ejected perhaps by migrating giant planets or by close encounters with other stars. They remind us that planetary systems are dynamic and that material is constantly being shuffled, lost, or exchanged. By studying such objects, we are glimpsing the common fate of matter across the galaxy. Our own solar system has likely sent countless comets and asteroids drifting into interstellar space. 3I/Atlas is simply a reminder that other systems do the same. This makes Webb's image not just a technical triumph, but a profound moment of connection. It is evidence that the galaxy is a shared environment, that the building blocks of planets, oceans, and perhaps life itself are not confined to one neighborhood. 3I/Atlas carries the story of another system, and through Webb, we are learning to read it. Every discovery made about its composition, structure, and path deepens the narrative of cosmic interconnectedness. The significance of this image also extends to the future of exploration. While Webb observes from afar, plans are already underway for spacecraft capable of intercepting future interstellar visitors. Missions like these would benefit directly from Webb's insights, using its spectral analysis as a guide to what instruments should be included and what materials to expect. The capture of 3I/Atlas in real detail sets a benchmark, proving that interstellar science is not a dream but a field grounded in tangible results. Culturally, the image has the power to inspire. Just as Hubble's deep field images reshaped public imagination about the universe, Webb's portrait of 3I/Atlas may ignite fascination with the idea of interstellar travelers. These objects are literal emissaries from other worlds, drifting across the void. To see one clearly, To know that it exists and that we can study it changes the way we think about the galaxy. It makes the vast distances seem slightly less abstract, the notion of other worlds slightly more real. The Webb image of 3I/Atlas will surely be revisited countless times in the coming years, each analysis peeling back another layer of mystery. But even in this first glimpse, the sense of wonder is undeniable. It is a reminder that astronomy is not only about cataloging and measuring, but also about moments of awe when the universe reveals itself in ways that surpass expectation. Webb has shown us the face of a wanderer from beyond, and in doing so, it has reaffirmed the human drive to look outward, to seek, and to understand. The capture of 3I/Atlas by the James Webb Space Telescope has not only offered a historic first view, but also unlocked avenues of exploration that branch far beyond the initial image. To extend the conversation, one must step into the intricate details of how this detection expands our scientific reach, how it challenges existing theories of planetary system formation, and how it reshapes humanity's philosophical relationship with the wider cosmos. What makes this event extraordinary is that it cannot be confined to a single field of science. Astronomy, planetary science, chemistry, physics, and even cultural thought are now tethered to the moment Webb first revealed this alien wanderer. The process of imaging such a distant and fleeting body itself deserves attention. Capturing an interstellar object is vastly more difficult than observing a stable star or a planet in orbit around our sun. Objects like 3I/Atlas move quickly across the sky relative to the background stars, and their faintness makes them difficult to isolate. Traditional telescopes can struggle to track them with precision, often smearing the object into streaks of light that tell us little about their structure. Webb, however, was designed with a remarkable suite of instruments that can adapt to track such targets. Its near-infrared camera, NIRCam, and near-infrared spectrograph NIRSpec were both employed to follow the object across the dark canvas of space. Engineers had to program Webb to adjust its mirrors and pointing mechanisms in real time to keep pace with 3I/Atlas, allowing astronomers to extract the first true image that does not blur or distort the subject. This adaptability has far-reaching implications. If Webb can capture an interstellar visitor with such precision, then similar methods can be used for other dynamic, fast-moving targets in our solar system. This expands its role beyond a telescope for distant galaxies into a vital tool for planetary defense, comet studies, and asteroid tracking. While the focus here remains on 3I/Atlas, the technological success has ripple effects that will enhance our readiness to observe future cosmic interlopers. The data that emerges from this image also stretches into the realm of chemistry at a scale never before possible for such an object. By splitting light through its spectrographs, Webb can reveal the molecular composition of the gases venting from 3I/Atlas. Preliminary readings have already suggested the presence of carbon-based compounds, silicate dust, and frozen volatiles like carbon monoxide and methane. These are familiar ingredients, but their ratios and isotopic signatures may differ drastically from what we know. Even tiny deviations in isotopic ratios can indicate that the environment in which these molecules formed was unlike anything in our own solar system. For instance, a higher than usual abundance of deuterium in water molecules would point to formation in an exceptionally cold stellar nursery. The scientific community now has a unique opportunity to compare these signatures directly with samples from comets captured by missions such as Rosetta and Stardust, bridging the gap between interstellar and solar system chemistry. Beyond chemical signatures, Webb's infrared sensitivity provides clues about the texture and composition of dust grains escaping the object. Infrared scattering patterns can reveal whether the grains are crystalline or amorphous, large or fine, compact or fluffy. These traits act as fingerprints of the physical processes that shape them. A predominance of crystalline silicates might suggest violent heating in the early stages of the parent star system, whereas amorphous dust indicates a colder, more gradual formation. These microscopic details, teased out from millions of miles away, deepen the narrative of 3I/Atlas as a carrier of alien geological history. One of the most compelling aspects of Webb's observation lies in its timing. Interstellar objects travel through our solar system at immense velocities. They pass close to the sun and then depart forever, never to return. The window for observation is narrow. sometimes only a matter of weeks. That Webb was able to seize the opportunity at precisely the right moment speaks to the coordination of the global astronomical community. Astronomers had to calculate the trajectory of 3I/Atlas with extraordinary precision, relay those calculations to Webb's operators, and configure the telescope for a challenging target, all within a compressed time frame. The successful image is not just a triumph of technology, but also of collaboration, showcasing the unity of scientific institutions across continents. The role of collaboration extends into the interpretation of the data as well. Once Webb provided the raw image and spectra, teams of specialists in various disciplines began their analysis. Astrophysicists looked at the orbital mechanics, chemists scrutinized molecular features, and planetary scientists studied the coma and tail structure. The image became the centerpiece of a global effort, pulling expertise from hundreds of researchers into a single conversation. This interdisciplinarity is essential because interstellar objects do not fit neatly into one category. They are both comet-like and asteroid-like, both familiar and alien. Understanding them requires dissolving the traditional boundaries of scientific specialization. Another dimension worth considering is how Webb's image reshapes theoretical models of planetary system evolution. Before Oumuamua was discovered in 2017, the existence of interstellar visitors was largely theoretical. Astronomers expected such bodies to exist but had never observed one. Theories held that planetary systems naturally eject material during their chaotic early formation phases. Giant planets sling small, icy and rocky bodies into interstellar space, leaving countless wanderers drifting between stars. The detection of Oumuamua and Borisov confirmed this idea, but Webb's capture of 3I/Atlas goes further by showing in detail what such an ejected fragment looks like. This evidence allows theorists to refine their models of how common these ejections are and what physical processes determine the composition of the survivors. If 3I/Atlas contains compounds similar to those found in our own comets, it suggests that planetary formation across the galaxy follows comparable patterns. That would mean Earth's chemical environment is not unique, and the potential for habitable conditions may be widespread. On the other hand, if its chemistry is radically different, it might indicate that our solar system is an outlier, shaped by rare conditions not easily repeated elsewhere. Either conclusion is transformative, pushing forward the debate about how ordinary or extraordinary Earth's emergence truly is. There's also the question of how long 3I/Atlas has been wandering. Based on trajectory analysis, astronomers can estimate that it has likely spent millions of years crossing interstellar space. During that time, it would have been bombarded by cosmic rays, exposed to extreme cold, and subjected to interactions with interstellar gas and dust. The weathering of its surface carries clues to the physical realities of deep space travel. Webb's instruments can pick up signs of radiation damage, unusual surface coatings, or altered chemical bonds caused by prolonged exposure to the interstellar medium. In effect, 3I/Atlas is not just a sample from another system, but also a laboratory specimen of what happens to matter adrift between the stars for geological time spans. The philosophical resonance of this discovery is profound. Humanity has always looked to the skies and wondered what lies beyond. To see 3I/Atlas clearly is to bridge that wonder with tangible reality. It is not speculation or imagination, but direct evidence that material from another star system is present in our skies. For poets, artists, and thinkers, this is fuel for reflection on our place in the cosmos. The sight of an alien traveler, caught for the first time in real detail, symbolizes both our isolation and our connection. We're isolated in the sense that interstellar space is vast, and these visitors are rare. Yet we are connected because their very presence proves that the galaxy shares its materials freely, that fragments of one world can drift into the domain of another. This connection also carries cultural weight. Images like this become part of the collective imagination, much as the Apollo moon landings or Hubble's deep fields did in earlier generations. They are touchstones for how societies think about the universe and humanity's relationship to it. The Webb image of 3I/Atlas will likely join that pantheon, inspiring new generations of scientists, engineers, and dreamers. In classrooms, it will be shown as the first clear picture of a body from beyond, a moment when humanity extended its reach across interstellar boundaries without ever leaving Earth's orbit. From a technological perspective, Webb's success lays the groundwork for the next generation of telescopes and space missions. The challenge of capturing fast-moving, faint interstellar objects is a preview of what future observatories must be prepared to handle. The European Space Agency and NASA are already studying concepts for rapid response missions that could intercept such visitors with probes. Webb's data will inform the design of those missions, particularly in terms of what compositions to expect and what instruments are best suited to studying them. The synergy between telescopic observation and spacecraft exploration is now more compelling than ever. Looking ahead, one cannot overlook the statistical implications of Webb's success. If we have already identified 3 interstellar objects in the span of just a few years, then the galaxy may be far richer in these wanderers than previously assumed. This suggests that the solar system is regularly crossed by alien bodies, most too faint or distant to notice. Webb's ability to detect and characterize them may help refine detection strategies, encouraging surveys to look for subtle signs of their presence. If these bodies are as common as early evidence suggests, then our opportunity to study them will only grow. The image of 3I/Atlas may, in retrospect, be remembered as the turning point when interstellar object science shifted from rare anomalies to a robust field of study. The educational dimension of this discovery is equally significant. Students of astronomy and planetary science now have before them a living case study in how scientific discovery unfolds. The story of 3I/Atlas involves detection, prediction, collaboration, observation, and analysis. A full arc of the scientific method applied to a phenomenon never before seen in such clarity. The image provides not just information, but also a narrative of human ingenuity and curiosity at work. The broader cosmic story that 3I/Atlas tells is one of exchange. Planetary systems are not isolated. They shed material into the galaxy, and some of that material inevitably drifts into the orbits of other stars. Webb's image shows that our solar system is part of a galactic network of material circulation. This is not merely a poetic thought, but a scientific reality. If fragments like 3I/Atlas can travel from one system to another, then the possibility of panspermia, the transfer of organic material or even precursors to life across interstellar distances, gains credibility. Webb's data on the organic compounds in 3I/Atlas will feed directly into debates about whether life's ingredients are scattered widely across the galaxy. In terms of long-term scientific planning, Webb's success may influence priorities in funding and mission design. The attention generated by the image of 3I/Atlas will likely encourage agencies to invest in instruments specifically tuned to interstellar science. Adaptive optics, rapid trajectory modeling, and flexible observation schedules will become increasingly important as astronomers prepare for future visitors. What was once a niche interest may now grow into a core branch of planetary science. It is also worth reflecting on the aesthetic and emotional qualities of the image itself. While scientists focus on data, the general public responds to the sheer beauty of what Webb has captured. Against the dark void, the delicate trail of gas and dust surrounding 3I/Atlas glows with faint light, a reminder of fragility and impermanence. This fragile appearance belies the immense journey the object has undertaken, but it resonates deeply with human observers who see in it a metaphor for endurance, travel, and the shared fate of all matter adrift in the cosmos. The story of Webb and 3I/Atlas is not just about discovery, but about perspective. It demonstrates that the tools we build, no matter how advanced, ultimately serve to satisfy the oldest human impulse, to look outward and to understand. With every advancement, from Galileo's telescope to Hubble's deep field, the universe has expanded in our minds. Webb's image of 3I/Atlas continues that tradition, showing that even in a universe of galaxies and quasars, a single small body drifting through space can command global attention and reveal truths about the galaxy itself. In the centuries ahead, this moment may be remembered as a threshold. Just as the discovery of exoplanets redefined our understanding of planetary abundance, the detailed imaging of interstellar objects may redefine our understanding of planetary system dynamics. Webb has given us the first authentic glimpse, and now the field is wide open. Other telescopes will follow, other missions will chase these wanderers, and the story will deepen. But the first clear vision belongs to Webb and to 3I/Atlas, and that is a moment that will remain singular in the annals of science. Through this lens, the event is not simply an astronomical milestone. It is a testament to what humanity can achieve when curiosity is coupled with perseverance, when collaboration bridges nations, and when technology is pushed to its limits. 3I/Atlas has traveled across light years of emptiness to arrive briefly in our view. Webb has ensured that its fleeting passage is not forgotten but immortalized in an image that will continue to shape science, philosophy, and imagination for generations to come. The Webb telescope's image of 3I/Atlas does not exist in isolation. Rather, it must be understood within the broader trajectory of how humanity studies the universe and the shift toward an era of precision astrophysics. While telescopes of the past gave us glimpses of distant galaxies, nebulae, and planets in our solar system, Webb is operating in a realm that straddles the line between cosmology and planetary science. The fact that it has successfully imaged an object as elusive as 3I/Atlas shows that it is not only suited for examining the farthest reaches of the cosmos, but also capable of focusing on the smallest and most fleeting of visitors. This dual capacity creates a bridge between the macroscopic and microscopic scales of the universe, allowing one instrument to connect cosmic history with immediate, tangible phenomena. One of the overlooked aspects of this achievement is the sheer challenge of differentiating 3I/Atlas from the background of stars and galaxies. Webb's detectors are so sensitive that every image brims with thousands of points of light, many of them ancient galaxies billions of light years away. Isolating a faint moving body within that ocean of light requires advanced computational methods. Teams use predictive orbital models to know precisely where Webb should look and machine learning algorithms to distinguish the faint trace of the interstellar object from unrelated sources. This is more than observational astronomy. It is computational astrophysics at its highest level. Without those algorithms and data pipelines, the raw information Webb collected would remain indecipherable. The image therefore represents not only the telescope's optics, but also the cutting edge of data science applied to space. Another aspect of importance is what the discovery reveals about stellar neighborhoods. 3I/Atlas did not originate in our system, which means it was expelled from another. Stars with young planetary disks frequently eject material as their giant planets migrate inward and outward. The result is a cascade of collisions, gravitational slingshots, and expulsions that send countless icy and rocky fragments into the void. By studying 3I/Atlas, scientists can indirectly probe the architecture of its home system. If its chemical ratios indicate heavy irradiation, that could mean it formed close to its star before being tossed outward. If its volatiles are pristine, it may have come from the cold outer rim, perhaps an analog to our Kuiper belt. In this way, Webb's image provides a fingerprint of a distant planetary system's dynamics, one otherwise invisible to us. This concept is crucial because most exoplanet systems we detect through telescopes are too far away to examine in fine detail. We know the mass and orbit of some exoplanets, occasionally the composition of their atmospheres, but little about their smaller icy bodies. Interstellar visitors act as messengers from those systems, carrying in their nuclei and dust the history of environments we cannot directly see. Webb's study of 3I/Atlas allows us to hold up a fragment of another world, as if the galaxy itself had mailed us a sample to analyze. That is a scientific gift that cannot be overstated. There are also astrophysical consequences of tracking such an object with precision. The orbit of 3I/Atlas is hyperbolic, meaning it is not bound to the sun. Yet the exact degree of hyperbolicity, measured with Webb's data, reveals how strongly it was influenced by the sun's gravity during its pass. This can refine models of how interstellar bodies are deflected as they traverse stellar neighborhoods. Understanding these deflections is not trivial. It teaches astronomers how interstellar debris might interact with exoplanetary systems elsewhere in the galaxy. Such encounters could deliver water and organics to young planets, seeding them with the raw ingredients for life. The path of 3I/Atlas across our solar system is, therefore, a small-scale rehearsal of how matter circulates across stellar domains. The cultural imagination is equally stirred by the idea of interstellar exchange. For centuries, humanity's stories about alien worlds and distant systems were purely speculative. Now we are observing matter from those worlds directly, not through science fiction, but through a telescope. This shifts cultural narratives from hypothetical visitors to confirmed evidence of cosmic sharing. Artists may find inspiration in the fragile arc of dust and gas illuminated by Webb. Writers may use the imagery of an interstellar traveler as a metaphor for migration, resilience, or the blending of different worlds. The image itself thus transcends scientific data and becomes part of the symbolic language of human culture. Webb's accomplishment also underscores the importance of timing in science. To catch 3I/Atlas at its most revealing phase, astronomers had to act while it was still close enough to the sun to exhibit activity. Too early, and it would have remained inert and faint. Too late, and it would have drifted beyond Webb's reach. This window of opportunity speaks to the agility of modern science. Observation proposals, telescope scheduling, and data processing all had to be mobilized swiftly. In earlier eras, the bureaucratic delays of coordinating international observatories might have caused the opportunity to be missed. Today's interconnected infrastructure ensured that humanity did not let this fleeting chance slip away. The Webb image also provokes new questions about how many of these objects exist and what role they play in galactic ecology. If interstellar visitors are abundant, then galaxies are constantly mixing their planetary debris. Our solar system, too, has likely shed trillions of objects into interstellar space. Somewhere out there, fragments of our comets and asteroids are passing by other stars, perhaps even being observed by civilizations if they exist. The capture of 3I/Atlas is, in a sense, an act of reciprocity. We are observing the debris of another system just as ours may someday be observed. This reciprocal perspective underscores the unity of the galaxy as a dynamic system of exchange, rather than isolated solar fortresses. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on James Webb's first image of 3I/Atlas? We want to hear from you. Thank you for watching, and see you next time.